Welcome to Ask and Learn.
This is another problem that winds up having some ugly algebra and trigonometry in here. So we have this rod here that's kind of supported by these two inclined walls, and so we want to figure out the angle that this rod makes with the horizontal, knowing the inclination of these two walls. And so the one wall has an angle of psi, and the other has an angle of phi, and then this angle here is going to be theta. So this force is going to be, so there's no friction on these, so this force is going to be normal to the wall. So it's going to have a magnitude F1 in this direction, and this is also going to be normal to the wall, so it's going to have a magnitude of F2 in this direction. And now I'm going to say this is my origin here. So theta, so R1 is 0. R2 is just this point out here, so L in this direction. We have the weight of this rod acting vertically, obviously, and then its distance from its position vector from the origin is just half of this, so half the magnitude because it's acts at the center, L over 2. But the same direction. So now we have all of our forces and our position vectors, and we can take sum the moments and sum the forces and sum the moments and set them to 0, and we'll get 3 equations and 3 unknowns. One equation is this, another equation is that, and the third equation is this. Now we can play a lot of we can do some manipulation here. We can basically use these two equations to solve for F1 and F2 in terms of W, phi, and psi. So here's what F1 and F2 look like in terms of those two. And obviously we could just put this one back in here. So again, they're pretty complicated functions of phi and psi, but if you check, they'll make sense. Like if you take phi, phi goes to 90 degrees, so we have something like this. Or, psi goes to 0, and phi goes to 90, something like that, which obviously in this case the bar would have to fall down because there's no friction here. So you can check various limiting cases to make sure that these things make sense. And we also get this other ugly trigonometric function that relates theta, phi, and psi. And again, you can use some trig identities and do a whole bunch of messing around, and and find that cosine of theta turns out to be this really ugly function of phi and psi. And there's not a lot I can say about this, but we can check some limiting cases. So the case when they're equal to each other, so like this, then theta equals 0, which makes sense. Okay? So that's good. If they're equal to each other, then theta should be 0. If either one of these angles is 0, if either one is 0, then we have an angle that winds up being this guy. We wind up having pi over 2 as our angle, so the bar is vertical. So you can see that by, if either one of these is 0, if phi is 0, then this whole function is 0, unless this bottom denominator is 0. I should have checked that. Let's see here. So this would be 1, so we'd have 1 here, minus 2 more, so minus 1, and plus 1. That's not good. So I didn't check that. So we wind up with a 0 over 0, do we not? Let's see here again. 1, these are all 1. So we get 3 minus 4 plus 1 is 0. So actually this is probably not correct, because I think what happens actually is I'm not sure what the limit of this is. I'm not sure what the limit of this guy is as either of these go to 0. But I think if you have one of them go to 0 and then the other one's like this, I suspect that what you'll either have is the bar lying flat or the bar. Well, the problem is that at that point things break down really, because you now you don't have point loads at the end of the bar, so the bar is in contact with either one of these walls at more than one point. So things kind of break down when you get to when you say either one of these goes to 0. Now again, you could say one of them goes to pi over 2 and see how that does, but that doesn't really help you, because then this becomes 1, and some of these become 0, and you still get an ugly function. So anyway, that's it's an interesting problem. It's a big mess of trigonometry, but here's your answer.